Mason Giacchetti, and I'm one of the collaborators on the reconstruction of top and anti-top quark events in the CMS detector through the use of graph neural networks project. Among myself are 4 other collaborators: Sean Flannery, Sagnik Balab, Dakshgard, and Mitchell Craven, along with our mentor AJ Wildridge, and we're doing this with a CMS collaboration who has generously provided us data for our work. So to start, I'd like to generally talk about what it is we're doing. And we're trying to, in theory, test what's referred to as the standard model. Now, the standard model of particle physics is physicists' best model so far for describing how fundamental particles interact and behave. Now, the standard model is really a composition of a variety of smaller theories which describe the various different particles and forces, and these theories are called quantum field theories. And in particular, what our research is interested in is one of these theories, which is referred to as quantum chromodynamics. Now, quantum chromodynamics is the theory that describes quarks, the fundamental building blocks of matter, make up things like protons and neutrons. It describes these particles' interaction via the strong nuclear force through a particle known as the gluon. So if you notice on the chart, the purple section, those are the quarks that we're interested in, and the gluon is what they interact with. Now, one of the things in particular we're looking at is the perturbation theory of QCD, which is how we approximate it, right? And because of our approximations, one of the predictions is that a specific type of particle, which I'll describe later, what's referred to as a toponium, shouldn't theoretically be possible. So it is our group's desire, hopefully, to sort of look for this particle, because if we can find it within the CMS detector, then it would suggest that our perturbation theories are slightly incorrect and require modification. And so that's generally the focus of our goal. Now, the CMS detector, just as a slight introduction, is the compact muon solenoid. It's a detector at the Large Hadron Collider. And it can, as the name would suggest, particularly looks for muons, but can observe other events. And in particular, toponium, which is a particle that consists of a top and anti-top quark, is what we're interested in, and in order to find it, we have to look for events within the detector that contain, as you might guess, a top and an anti-top quark. The problem is that if we're looking for these events, right, looking for the top and anti-top quark events in the detector, it requires that we have the decay products, because they decay so quickly that the detector never actually picks up on them. It only picks up on the decay products, which don't decay by the time they get to the detector. But the issue there is that some of the decay products, such as neutrinos, are notoriously difficult to detect, if not impossible, with the machinery at this detector. And thus, we need to develop techniques of being able to kind of imply the existence of these neutrinos from other data so that we can actually reconstruct the top and anti-top quark events to look for toponium. And we use neural networks for that. But just as a slight overview of what toponium is, you have particles in the standard model, and they have corresponding antiparticles. And so with the quarks, you can have a quark interact with its own antiquark, and that's what we call a quarkonium. Now, for all the quarks, that is possible, except for the top quark, because it's so heavy that it decays before it should have a chance to interact. So by looking for toponium, if we are to find it, it suggests that our predictions made by quantum field theory, the perturbation of quantum chromodynamics, rather, are incorrect, and thus would suggest areas of improvement. And so to look for these neutrinos which are missing and which are vital to finding the top and anti-top quark events, we're using graphing neural networks. And essentially the way general neural networks work is you have a bunch of input layers. Your data takes your data, and through a series of weights and biases and the relationships between these, this data gets processed through a series of hidden layers and essentially tries to classify some outcome. So, it could be identifying digits, handwritten digits. It could be identifying facial expressions, things like that. We're hopefully trying to use data from the detector, things that are detected, to classify whether or not we should have expected to see neutrinos. And if we can predict the neutrinos, then we can work back and try and look for the top and anti-top quark events, which we need to look for toponium. And so far, we've practiced with developing neural networks and machine learning algorithms that take data and can produce accurate predictions, because we need to modify the weights and biases, but we can't do that manually, so we use machine learning. So we've tested different forms of optimization, such as atom optimization and things like that, and have been experimenting with ways to maximize the efficiency of our machine learning and of our neural networks, and so we've been playing with the designs of those. But overall, that's the focus of our research, which is to try and identify toponium events, and to do so, we have to reconstruct top and anti-top quark events, and to do that, we have to kind of reconstruct neutrinos, which we'll be using graph neural networks for. So that's our project. Thank you very much for listening.